My name's PJ Jayawardene. I head all the 5G R&D at Charter Communications. Joining me today, we have Mo Daoud and Kashif Shakil. We're going to talk about fixed wireless access using CBRS. In the cable space, the first question that comes up, we think wireless, it's Wi-Fi, but things are transitioning because of the really expensive asset that you should procure to make a wireless network was spectrum. With Citizens Broadcast Radio Service, there's a framework that's put in place for us to do shared spectrum. So for anybody that wants to offer wireless broadband, that really expensive proposition of buying spectrum is no longer there. There are some caveats to that, which I let these two gentlemen go in detail. Much like any of life's problems, just before you tackle it, you have to ask, why do I need to do it? And the next question is, how can I do it? So today's discussion about fixed wireless access using CBRS, we'll aim to answer those two questions. The why will be answered by Kashif Shakil, and then followed by Mo Daoud, who'll talk about how we've done it. If you look at the introduction for the session, was to give some actual practical examples of how you can make this work and why it's actually relevant for the cable operators, for the MSOs. But before we do get to that part, let's answer the question, why should we even look at this? And to make some very compelling arguments, I've got Kashif Shakil, Director for Sales and Solutions at Ericsson, sorry. And let me get you set up over here, Kashif. Hopefully it'll work. And let's get the first slide going for you. I've been warned that this clicker is a little bit funky for the first slide. She is right. Here you go.
Thank you, PJ. Good morning, everybody. My name is Kashif Shakil, as PJ said. I work in Ericsson. I have been doing fixed wireless for some time with few customers and looking at fixed wireless for CBRS in this presentation. So first off, to start things off, I wanted to say that home broadband is still a good opportunity for operators who are looking to grow revenues. And the reason is that there's still options to provide coverage in underserved and unserved communities. There's quite a bit of them. Other operators are looking at injecting new competition in markets that are actually well served today. So something that we have to be mindful of if we're not even going in those markets with fixed wireless. There are several options for providing broadband service. You guys are already in that business. In this presentation, we're going to focus only on the wireless as 3GPP, LTE, and 5G wireless. And there's two segments here that we will look at. We will look at the rural areas, rural markets, and the suburban and the urban markets. In rural markets, fixed wireless makes quite a lot of sense. And the reason is you don't have to dig holes, you don't have to run wire, and in rural areas, that can get expensive. So in most cases, fixed wireless works very well in rural areas. In suburban and urban areas, the game is not about just getting service. It's also about throughputs and speeds and things like that. And we have now new technologies within LTE as well as within 5G that enable those high speeds. Things like massive MIMO, things like millimeter wave spectrum. We're going to talk in more detail about those technologies, but keep in mind that operators are using those technologies to also go into suburban and urban areas to provide home broadband. Okay, so in this presentation, we're going to ask three questions. First, is there a viable business case for fixed wireless before we start indulging in it? We're going to also answer what are the key enabling technologies, and then would also like to cover a little bit on, is it working somewhere else? We don't want to be first. I can tell you that it is working elsewhere in the world as well as in the US. We'll discuss that. What is driving fixed wireless access? Why is it gaining momentum? There's 4 factors that are converging. The first one is new spectrum. PJ talked about spectrum being the key asset when it comes to wireless. And in the US specifically, we have CBRS spectrum that is becoming available. And this is unlicensed and lightly licensed spectrum. We expect in rural areas there's going to be a lot of it available, and you may not even need to acquire the license because it's 150 megahertz. And so this license is becoming available. It may be not 100% free, but it may be quite inexpensive. Then there are technology advances. We'll talk about those with LTE Advanced as well as 5G. There's a global ecosystem that has already developed. People have been doing fixed wireless globally elsewhere. And so we have specifically for CPE or UE devices, the things that go at home for fixed wireless, there's a good ecosystem for that already, which we can leverage here in the US now. There's government investment. If you guys are familiar with the CAF program that government has rolled out to provide broadband coverage in rural areas. Recently, Mr. Trump has announced also $20 billion that he wants to invest in rural communities for broadband. There's things coming together for enabling broadband now in rural areas specifically. All right, let's talk about how fixed wireless solves some of the issues and problems that operators are facing. The chief among them is legacy technologies. There may be a path for enhancing and enabling legacy technology, there may not be. It depends from operator to operator. With wireless, you can leapfrog those legacy technologies and provide the throughput and the coverage that is required. There's also competition for bit rates, especially in the suburban and the urban areas. It's not only about getting broadband, but it's also about getting broadband at 50, 100 megabits per second. And here, with LTE Advanced and 5G, we can provide those rates. With 5G, millimeter wave 5G, we can provide gigabits per second type of rates. And we talked about the deployment costs for rural. Those continue to be an issue, running wires, digging holes in the ground, things like that. With wireless, as you may imagine, you don't have to do that. That gets you to market early. You can generate revenue earlier. If there's churn in the market because you're an operator that is not providing, let's say, the right throughput compared to competitors, you can get to that earlier and reduce churn. Those are all the things that fixed wireless can help. Okay, so looking quickly here at the economics of fixed wireless, there are several factors that an operator has to consider. Chief among them is the cost of spectrum. Spectrum is the lifeblood of wireless, as you know, and cost of spectrum can be a roadblock. As I mentioned before, with CBRS, we're kind of solving that problem a little bit. We have to consider the cost of cell site CapEx, both CapEx and OpEx. We have to be mindful of that when we're putting together business cases. One factor that sometimes gets ignored is the cost of customer premises equipment. And it's just not the cost of equipment, but also the truck rolls that you have to do. If you're going to deploy, let's say, one cell site for fixed wireless, you may have to do 100 or so truck rolls for deploying CP devices to customer premises. And so we have to be mindful of that, the cost of the CP itself, as well as the cost of deploying it. And there are innovations in how we do that to reduce that cost. Technology choices, we recommend highly that 3GPP, not because we're a 3GPP vendor, but also because there's economies of scale in 3GPP that can help you with driving down costs. One important factor also is subscriber density. The sparser the grid that you're trying to cover in terms of households, the more difficult the business case can become. And then operator, the ambition to have certain market share is also important. If you're going for 10% market share, maybe the business case is not going to be so good. So we advise to have an ambition for a higher market share. You can capture more of the homes in your coverage area. And then people are using broadband at increasingly higher rates, so the traffic growth is an important consideration in business cases. So does the data rate offerings. Together, these factors come together, and can affect the business case, and it's different for different operators, so something that we have to do individually for our own purposes. Here's an example of a business case we have done with an operator. This is done with market pricing, with the regular kind of network design and things like that. We arrived at, and this is for suburban and also rural, half and half split. There are 600 homes per square miles for the suburban morphology, and 10 homes per square mile in rural for this case. We arrived at about $300 of cost per home passed, and more importantly, cash flow positive in 3.5 years, which is great. And we can start deploying for this operator whenever CBRS becomes available. And it actually is, we're going through initial commercial deployments for CBRS. We expect sometime within a month or so for GA portion of CBRS, the unlicensed portion, to be available. So faster time to revenue, faster time to market, and positive business case for this operator. I'll show you examples of different business models that operators throughout the world have been using for fixed wireless here. The first one is this NBN project that we have been working with Australia for quite a while here. This is a rural fixed wireless in Australia type of network. It covers basically everything except for the coasts in Australia. As you know, most of the population there is in the coast, and there is not a very strong business incentive to put wires in the interior of the country. And that's why NBN was formed, and they're providing that broadband service to homes and businesses there in Australia. It is about a terabyte of data per month and up to 100 megabits per second of service, so it's pretty fast considering that it's rural. It's been working quite for some time. It uses TDD spectrum in mid bands, which is 2.3 gigahertz band there. And we have been providing equipment for that, as well as we do services for this, managed services for this NBN operator. Another example is fixed wireless, a purpose-built fixed wireless network in millimeter wave for urban. And this was what was launched by Verizon. You may have been familiar with and reading about it in press. It's based on 5G millimeter wave, and it's meant to target urban, high data rate type of subscribers. Finally, this third operator is doing a converged mobile broadband and fixed broadband service. So they have a mobile network for mobile broadband already, and they're offering up to 200 gigabytes of data buckets for just data fixed wireless. And the devices are your MiFi devices, home routers, and things like that. So this is a different business model. They're leveraging their existing mobile broadband network for fixed wireless. So the point here is that different operators are experimenting and providing different business models in the market out there, quite successfully so. From a perspective of deploying fixed wireless networks, we see two, from a CPE perspective, we see two major strategies. The first strategy is to have a outdoor mounted CPE, and that's typically on the rooftop of your house or on the wall or something like that, which is outside of the home. The second strategy is for the subscriber themselves to mount CPE wherever they like. It's self-installed for the subscriber. We see pros and cons for both. For a subscriber-managed CPE, we see that it may impact network capacity, network performance. But as I said before, cost of going to homes and installing CPEs can impact your business model, business case. So there's a give and take here. And as an operator, you have to decide for yourself what is best for your particular situation. Outdoor mounted CPE for best network performance, best capacity from the network, least investment on the network, but more investment on the CPE side. And then with the subscriber managed CPE, then it's the other way around. More network investments, but less CPE investment. So whichever way the business case works out. In this presentation, I'm going to focus on a model where it is an outdoor operator-mounted CPE. In CBRS, a lot of operators are actually going with that model, which is outdoor mounted CPE managed by the operator and installed by the operator. Okay, so it's mounted at the top of the home, as you can see over there. And then the wire is brought, LAN cable is brought up to home with a FWA gateway, and then services are provided to the subscriber over Wi-Fi or fixed network there onwards. Okay, so we're starting CBRS with LT, and we're going to go with 5G in CBRS as well. What changes with 5G? We have millimeter wave spectrum in 5G. That's where we're starting with. We're going to migrate existing mid-bands over to 5G as well. But we're starting with millimeter wave. That's a lot of spectrum, means a lot of throughput. 5G also offers ultra lean design, so that we're not wasting a lot of bits out there for common channels. We're dedicating to traffic channels. And so the spectral efficiency of 5G is supposed to be better. Then we have better multiple user MIMO. I'll talk about that in the coming slide. We have multiple user MIMO in LTE, but we have improvements in 5G, which further improves performance. And there's dynamic TDD in 5G. What that means is, depending on your traffic demand, the TDD profile may change. You may dedicate more resources to downlink, less to uplink. In some cases where the more uplink demand is present from the customer, then you may dedicate more resource to the uplink and lower to the downlink. It's flexible in 5G. So one question that I get asked is, well, 5G millimeter wave, we've heard about it. It doesn't cover that far, doesn't have a good range. So what do we do with that? Some operators are considering combining millimeter wave 5G with mid-band, let's say CBRS. And what is the benefit of that? It actually helps you improve the range of 5G, millimeter wave 5G, if you do that combination, that carrier aggregation. So over here, we're showing here that this is kind of the oval here with the coverage for millimeter wave 5G. And then when you combine it with mid-band in LTE, then you see the coverage actually improves. And how does that happen? It's because these networks are uplink limited. With mid-band, the uplink goes farther. If you get the mid-band from mid-band, the uplink from mid-band, and the downlink from millimeter wave, you get the best of both worlds. When we combine 5G millimeter wave with NR mid-band, because of the better spectral efficiency in NR, you get to extend coverage a little bit more. So this is a strategy where we use millimeter wave together with mid-bands, get the best of both worlds, extend the coverage of millimeter wave, and make millimeter wave more viable for fixed wireless. Not only for urban, but also perhaps for suburban. Okay, so quick word about CBRS, 150 megahertz of spectrum. We are going through initial commercial deployment right now. We will have the unlicensed piece of it called GAA available within a few weeks for commercial services. And then PAL auctions are now slated to be happening next year. There's 70 megahertz of PAL licenses that will be available if you want to lock down spectrum so that nobody else can use it but only you. Then the mechanism for that is PAL licenses. GA is available to everybody. Okay, so finally, I think this is the last topic before we go to summarize things. Massive MIMO, what is that technology? So with massive MIMO, we use more than 8 antennas, typically 32 or 64 antennas on the base station. In a traditional system, we do something like this. If you have, let's say, 4 antennas or 2 antennas, we broadcast the RF signal all over the coverage area of that cell. And even though my users are only here, I'm kind of wasting some energy transmitting in areas where there are no users. With massive MIMO, I can form narrow beams, as shown over here. And in those narrow beams, I transmit signal only to the places where the subscribers are present, where the homes are present. What that does is it enhances signal strength and consequently signal to interference ratio for those homes. And higher SINR, signal to interference ratio, means higher throughput. So just by doing that, I improve throughput. This is the basic concept of beamforming. Now I can enhance it further by using what is called multiple user MIMO. What happens here is, if you compare it to the previous slide, you see there are different colors here. These colors represent different frequencies and time slots for the transmissions. So let's say I have 20 megahertz of spectrum. Conceptually, I split it, let's say, three ways and provide it to these 3 different homes. With multiple user MIMO, I'm not splitting spectrum, I'm not splitting time. I'm actually using the same inter-interface resources in terms of frequency, in terms of time, and then reusing them between all these different homes. As long as these homes are spatially separated, they don't interfere with each other, I can perfectly use all the spectrum for all the homes. That's why it's called multiple user MIMO. It has an impact of increasing not only system capacity, of course, because I'm multiplying the resources that I have, but also coverage. And it's a key technology for LTE, fixed wireless access, as well as NR, fixed wireless access. Okay, so in LTE, I can do beamforming and multiple user MIMO especially beamforming in the downlink. In 5G, I can also do beamforming in the uplink. So there's further improvement because of that. Here's an example. So this is my traditional site. These are concentric circles of throughput, going from high throughput to low throughput with a 44R 4 antennas system versus a 6040, 64R a massive MIMO antenna system. And you can see that with 6040, 64R, I can extend the coverage and the capacity of the system. This slide is really about coverage. I can extend the coverage of the system. So in a rural deployment scenario where you are maybe coverage limited, 6040, 64R massive MIMO system can help you extend that coverage further, in addition to giving you the capacity gains that comes with multiple user MIMO. Okay, so to conclude, fixed wireless system is ready. All the technologies is there. The products are there. Network products are present. You can also get CPEs from the market. It's ready to go. Operators have been experimenting with this, and not only experimenting with this, but for some time providing commercial service for fixed wireless access throughout the world and also in the US. And it's an opportunity for cable operators as well today to leverage this technology to extend your plant where it's not maybe economically feasible right now, and even to compete in areas where you have a strong competition with other incumbents. One of the things we hear from some wireline operators is fixed wireless also allows them to extend their coverage outside of their LAC or franchise coverage area, because they have limitations otherwise. So a lot of things are coming together for fixed wireless, and I hope you can use that also for improving and enhancing your guys' business as well. Thank you.
Thanks, Kashif. Thanks, Kashif. Let me get Mo set up. So the format that we'll follow is after Mo does his presentation, then we can get around to a Q&A session. So now to explain the how and give some examples of actually doing fixed wireless access using some of his own personal experience with the trials. Mohammed Daoud, will you join me over here? Thanks. This side. There you go.
Thank you, PJ. Thank you, Kashif, for the great presentation. My name is Mohammed Daoud. I'm a principal engineer in the wireless R&D department at Charter Communications. And what I'll do is that I'm going to build on what Kashif told us. He told us about the business case. I want to show you real numbers from the field, coverage and capacity numbers from all our testing that we've been doing for the past 2.5 years. So first I want to start by CBRS. I don't want to spend much time on this slide because Kashif did a great job explaining what CBRS is. What I want to note here is that the band itself is is the laser pointer working? The band itself is 3.55 to 3.7. It's not a new band. What's new here is the sharing framework. This is what's new here. This is the innovation part. The SAS, the sharing framework of the CBRS. Other point I want to note is that PAL licenses. Auction will be June next year, and you will be county-based, 7 licenses per county. And as an operator or as a bidder, you can only buy 4 per county. You can't get the whole 7. So these are the 2 things I want to note in this slide. Here I want to talk about fixed wireless access networks versus regular LTE network. The main difference is that in a regular LTE network, you have user equipment or a handset. In the CBRS or the FWA, you have a CPE, customer premises equipment, where you put it on the rooftop of the house or in the side of the house and you try to aim it toward the tower. So the main difference is that the X2 interface will not exist. There are no handovers. Of course, the CPE will never move. The house, of course, never moves. So the interface itself, we don't really need it. Other than that, it's a traditional LTE network. And in this presentation, I want you to leave this room remembering 3 things. Number 1, that FWA coverage is heavily dependent on the environment. And number 2, that there are so many technologies within the 3GPP that will help you enhance your FWA performance. You have to pick and choose wisely. And number 3 is that network planning, it may seem easy because you know where each CPE is all the time, but we'll show you examples how it can get very, very tricky. So pay extra attention to the sector capacity. So these will be my 3 themes for today that I'll be covering. And let's start by theme number 1, which is FWA coverage is dependent on the environment. FWA coverage is dependent on the environment, the terrain effect. I'm going to give you 2 examples from the Denver trial. The first example on the left-hand side is testing we did in our office in Denver. We put a radio on the rooftop of one of our buildings. And if you've ever been to Denver, you know that it's a hilly terrain, a lot of ups and downs. And what we wanted to see is that what is the coverage? So we put this radio on the rooftop. We had our test van that you saw in the previous slide. We kept going, and every almost half a mile we stopped. We raised the mast of our van. We had a CPE on it. And we're measuring the RF and the throughput. You would expect that the further you go away, throughput will drop and RF will drop. But we saw 2 big dips here. That I want to note here, these 2 big dips. So we went back to our office, we were trying to understand why did we see 2 big dips and then the throughput and the coverage, RF conditions went up again. The first dip, when we went back to our office, we looked at the terrain profile. As you can see here was our radio. The CPE was at a much higher elevation. So of course, most of your signal was blocked by the terrain. The next point where we had no coverage at all, this was 2.5 miles away, was the same exact scenario, where the radio was a little bit down here, and CPE was much upper, and there was a little bit of a hill here. So that's why we had no coverage at all and no throughput. But when we went a little bit away, our RF conditions got much better. At this point, we did not see the same terrain effect. The other example I want to give you about the terrain is also from Denver. In Denver, we have an employee trial where we give some of our employees some CPEs to put on the rooftops or on the side of their houses. And this is one of the sectors we have. And again, we saw very similar things. You see the 1.1 mile, we have an employee with a CPE at 1.1 mile getting minus 117 RSRP and 12 SINAR, while at the 4.7 mile away, another one is getting minus 97 RSRP and 28 SINAR. Again, this is puzzling. So we went to one of our RF planning tools. We saw this employee, although he's very close to a tower, he's getting more than 50% Fresnel zone blockage here. The one which is far away is getting less than 10% blockage. So this is what we want to note from this slide, is that the terrain will play like a major role in blocking your signal. So don't expect that the closer to a tower you get more throughput, the further away you get less throughput. Under the same theme, which is FWA's environment dependent, I want to talk about the weather effect. We got a question from our leadership. What is the rain effect on CBRS signal? The first thing that came to our mind is that it's not millimeter wave, so we should not see much, deviation. However, we wanted to prove our theory, hypothesis. So this testing was very, very tricky to be done. We had to go to Michigan around January timeframe, and we had to check the weather to know which days it will rain and which days it will not rain, and go to the same exact places, raise the CPE to 12 feet and 25 feet high, and test during the rain days and non-rain days. In the papers that probably most of you have seen, I have more examples, but here I'm giving you about the 0.8 mile cell near example. We recorded 3 things: RSRP, and we saw that the maximum deviation was around 3 dBm. SINAR, 3.5 dB, throughput 2 megabits per second. So we concluded that the rain has little to no effect on our CBRS signal, and the same was seen at cell middle and cell far, which you'll find in the paper you get. Under the same theme, which is FWA environment dependent, is the foliage effect. And the importance of this foliage effect is that CBRS FWA is mainly for rural environments. And in the rural environments in this country, many places has so many trees, very high trees, and a lot of foliage. So we wanted to understand if we will deploy in such a place, what should we expect? We went a little bit north of Tampa, a couple of hours from Tampa. We chose those test points very carefully. So these two test points here are in a very dense tree areas. And what we found is that we put also our radio on one of our towers. We had our test van. We kept going far away. At these 2 points where we're under the tree line, that the trees were more than 25 feet high, raising the CPE did not make much of a difference. 12 feet CPE, 25 CPE were already blocked. The signal was very bad. When we went a little bit far away at this point, with no foliage, the throughput increased. So what we concluded here is that when you are at an area with very high trees, try to install your CPE at or above the tree line. The conclusion of my first part of the presentation is that terrain, friendly zone blockage will affect your coverage. Rain has little to no effect on CBRS RF conditions. And cell radius will shrink in high foliage areas. So try to install a CPE at or above the tree line. I promised I'm going to talk about 3 themes. So theme number 2, which is FWA technology enhancement. There are so many different technologies within the 3GPPs that we can use and we should use to enhance our FWA performance. This test was done 2 years ago. There was no beamforming LTE radios at this time. So we worked with one of our vendors, their proprietary technology, non-3GPP, but they had a beamforming radio, 16 active RF chains. And what we wanted to understand is beamforming versus like regular macro, when to use which of these, and what's the beamforming gain that we can get. Before getting into this slide, into the graph itself, I want to note something very, very important here. The beamforming radio is transmitting at 43 dBm, while the regular macro was 47 dBm. What does this mean? It means that the beamforming radio is transmitting at less than half the power. Every 3 dBm is doubling the power. So we're transmitting at less than half the power of the regular macro, and it outperformed at these 2 locations here. So at the first location here, the orange line is a beamforming radio, which is transmitting at less than half the power. And this point, I remember it very well. It was an urban area where we were behind the building. And as you can see, it's outperforming the regular macro. And this other point here was also in another residential area. The macro could not connect at all, while the beamforming radio had 27 megabits per second. And again, this is when beamforming is transmitting at less than half the power. And we concluded that beamforming will help you to have an attach in a hard-to-reach places. Another technology I want to talk about is a massive MIMO. And again, this test was done 2 years ago. This was one of the very first massive MIMO radios out there in the market. And we wanted to understand when to use a massive MIMO, when to use like a regular macro. We wanted to understand what's TM7, single-user MIMO, TM8, multi-user MIMO. We had so many questions. But I choose to just show you this slide here. The rest, I think I mentioned the rest in the paper. So the reason I want to show you this slide, because we had on one of our towers a regular macro and a massive MIMO 64T, 64R. We went to a cell middle, 2.5, at RSRP was minus 119. The regular macro slightly outperformed, and I'm saying slightly because it's 10% difference. This is 42 versus 48 megabits per second. However, at cell edge, every single time we tested, we've seen at least 50% gain using TM7 single-user MIMO. You should not expect the RSRP to increase, but what increases here is a SINAR, which then will increase the modulation scheme, which will increase your throughput. So we concluded from this test is that TM7, the single-user MIMO, would be very, very beneficial for cell edge users who are already having bad RF conditions. And the third thing I want to talk about in the same theme, the technology enhancement, is that you should think out of the box. You could combine the CBRS with other different unlicensed bands. So what we did here, worked with one of our vendors. We combined CBRS radio with a 5 gigahertz radio. 5 gigahertz is an unlicensed band used by the WISPs, usually in rural environments. And what we wanted to see here is two things: more speed and more link reliability. More speed because you're having speeds from the 5 gigahertz and from the CBRS combined together, and reliability in case one of the radios fail. And we have seen this at 3 miles. 5 gigahertz radio failed, CBRS radio was still up, the end user, which is the NCPE, still had coverage. The importance of this method we're trying to do is that if you are a WISP and you are only using GAA, you are in an area where there is an incumbent that can come in any time. The SAS may take your GAA channel. Your end user will have no coverage at all. So you have to combine, or you have to think about innovative ways that if you lose your GAA channel, what could happen? And this is what we're thinking here, combining it with other unlicensed bands. So the conclusion of my second part of the presentation is that beamforming will help with connectivity in hard-to-reach places. Massive MIMO, especially TM7, is good for cell edge users to increase their throughput and SINAR. And combining CBRS with other bands, it can be 5 gigahertz, can be TV white space, whatever, will increase your link reliability and throughput. The third part of my presentation, the third theme I want to talk about, is the dimensioning. And to give you the example of dimensioning, I want to take you back to Denver. In Denver, we had multiple sectors, but I want to show you only 2 sectors here. So this one we were calling Sector 1. As we see, Sector 1 is only serving probably 6 of our employees here. When each of the employees doing maximum throughput alone, they're getting very good high throughputs, 200 megabits, 90s. But when all of them are doing maximum throughput at the same exact time, the throughput drops. Because the scheduler of the ENB have to start distributing the resource blocks to all of them. However, in the case of Sector 1, all of them were still above 25.3. Significance of 25.3 is that this is the definition of broadband for FCC. 25 megabits on the downlink, 3 megabits on the uplink. What about the other sectors then? Sector 2. So this sector was serving probably around 11 of our employees, when each of them doing maximum throughput alone, also very good speeds. Let's see when all of them are doing maximum throughput at the same exact time. Many of them will drop below 25 megabits per second, which is a definition of the FCC, again, of the broadband. So what does this mean? This means oversubscription. We have to do oversubscription when you dimension your network. And oversubscription literally means that you can add more subscribers because not all of your subscribers will be doing maximum download even at your busiest hour. But choosing this oversubscription factor is more of an art than science. You don't want to put like a very big number for oversubscription, which will decrease the quality of experience of your subscribers. You don't want to put a very small number that may leave your sector underutilized. So of course, every different operator will have like different value for this over-subscription factor. Another thing under the same theme of the network dimensioning is the sector capacity. So working with one of our leading vendors, we know that the 40 megahertz channel on a 256 QAM theoretically would give you 300 megabits per second. We said, okay, let's see this in our lab. We have a very nice lab in Denver with RF chambers, and we did not see it. We only saw 285 megabits per second, which is expected. You never see the theoretical maximum. We said, okay, let's go to a field now. I want to see the 285. We took 10 CPEs in one of our test vans at 256 QAM, very good RF conditions, and we did not see it again. We saw 253. The sector throughput dropped to 253. And again, this is expected. In the field, you see much less than the lab. And we said, let's do another test. Let's go like a little bit further away, in a place where it's 64, 16 QAM. CPEs, are different RF conditions. 111. So what I want to show you from this slide is a 40 megahertz channel, which is your main resource when you're deploying any network, the same 40 megahertz channel. You could get 285, you could get 253, you could get 111. How can you get these? It depends on where your subscribers are. Are they in good RF conditions? Are they in bad RF conditions requiring more resource blocks? So this is the planning part of it. And the 40 megahertz channel, if you are buying 2 PAL licenses and depending on 2 GAAs, these are very, very scarce resource. So we want to understand more about the sector capacity, like how to do it in real life. And luckily, we have our Denver test bed, so let's go back again to Denver. So now I took you to Denver, took you to a sector that had 11 of our CPEs, And as you can see here, we plotted the QAM modulation. We have 3 at 16, 3 of them at 256, and 4 at 64 QAM. So the sector throughput here was 220 megabits per second. We said, okay, let's do our test again. Let's insert extra 10 subscribers to this sector at 64 QAM. The sector throughput dropped to 152. Again, because the InnoDB has to give all those resource blocks to all the subscribers. So we said, okay, we want to understand a little bit more. Let's take those 10 CPEs out and put 10 different CPEs at 256 QAM. What happened? The sector throughput went up to 227. And I just want you to take 1 minute here to think about this. 2 slides ago, I showed you 11 CPEs at 220 megabits per second. Now I doubled the number of CPEs in my sector, and I increased the sector throughput. Think about this. Doubling the number of CPEs in your sector and increasing the sector throughput. And why did this happen again? Is that those new CPEs are at good RF conditions. The point we're trying to make here is that when you deploy, try to make sure that all of your subscribers or CPEs are at 256 QAM, 64 QAM. Try to avoid 16 QAM, and of course, no QPSK QAM. Maybe those QPSK and 16 QAM subscribers could be served by another sector, or don't even serve them at all, because you will drag your sector throughput down. So although you know where each of your CPE will be all of the time, and you know their RF conditions, it's very, very tricky because you have to make sure that they are at good RF conditions when you decide to give them service. So at the end, I want to remind you of the 3 things that I want you to leave with. The 3 things, again, they were that FWA coverage is heavily dependent on the environment. We've seen some example of terrain effect, weather effect, foliage effect. The second thing I wanted you to remember was that there are different technologies within the 3GPP. Use them wisely. Think of it as like a toolbox of different technologies, massive MIMO, beamforming, macro, when to use which technology. And the last thing is the sector capacity. Pay extra attention to the sector capacity. You paid so much money for the spectrum, or GA or SAS is giving it to you. So try to deploy your sectors by putting most of your subscribers at good RF conditions to increase your sector capacity. And finally, I just want to say that MSOs like Charter can leverage the vast fiber network to use it as a front haul and a back haul, and of course the Charter-owned towers to provide CBRS FWA service and help bridge the digital divide in this country. Thank you so much, guys.
Thanks, Mo. To get the discussion going, I want to go back to some of the material that Kashif presented first. You talked about key things, Kashif, that sort of drive the business case for fixed wireless access. What do you think? You mentioned about 3 or 4 of them, but what are the ones that move the needle the most? The key factors that make the business case for fixed wireless access be successful or make it a failure? What are the key things for you?
Yeah, first I should say that because there's so many networks out there in the world doing fixed wireless, there is a positive business case. People are making money out of fixed wireless. So having that in background, there are obviously the big things are the cost of the network and the cost of the CPEs. What people tend to ignore are things like the installation cost for the CPEs, the truck rolls and things like that. People sometimes tend to focus only on the network costs, but those costs can get ignored. So that's important to consider in your business case. Then when you're putting together a business plan, you have to think about your ambition for how much penetration you wanna get, what is the market share you wanna get, and what type of users you're going to cover. The more sparse it is, the more difficult the business case becomes. And then finally, you have to think about government subsidies. In a lot of cases, for those sparser areas, there are government subsidies available. More are going to become available, we think, that can help your business cases.
Okay. And then, Mo, for you, looking at some of the learnings in actually how you deployed the network, how do you see, as more and more people get in, it's a shared framework, right? And you talked about massive MIMO and how you can manage interference and how all that's important. How do you see all of that coming into play as you start adding more and more operators offering the same service in a shared framework? How do you maintain the quality from what you've seen? What are the challenges and how do you overcome that?
Of course. Interference probably will happen if you're using GAA only. If you're using PAL, it may not happen, but in GAA situation, interference will happen. And that's when something like a massive MIMO, you have like those very narrow beams, can help mitigate the interference. And also the example we gave where you combine your CBRS with another technology. So let's say, back again to example I was giving, CBRS and 5 gigahertz. If the CBRS is having some interference, probably the 5 gigahertz is not having the same interference. So I'd say these are two very important things, the narrow beams and the combination of different technologies together to serve your end subscriber.
Okay, well, that's good. Over to the audience. Any questions that you guys like to bring up? Please.
You know, I just wonder, is there any, you talked a lot about the 5G and LTE, 5G new radio and LTE. Do you think that, I've been hearing a lot about the Wi-Fi 6 and 802.11ax. Do you think that has a place in providing a simple or, maybe cheaper approach to fixed wireless access, over a licensed or licensed spectrum, but, rather than using the, big heavy telco infrastructure, I just wonder if the AX would give you any advantages or disadvantages.
Yeah, absolutely. So first, let me say the fixed wireless is about SLA. And unlicensed spectrum has a place, but at the end of the day, you want some license guarantees. So you have the SLA that is met with the customer. In terms of unlicensed spectrum, what we recommend is the use of sometimes license-assisted access, which leverages the 5 gigahertz spectrum and can provide throughput boosts. Keep in mind that when you're establishing fixed wireless networks, you're trying to cover large amount of area, and with the unlicensed spectrum, there is the limitation on output power. And the ERP, which is 36 dBm, which is quite a bit less than what you really need for outdoor coverage. And so within those limitations, your coverage footprints are smaller, you need to build more sites, the business case may not really work.
I was talking about but you could run that over licensed spectrum as well. I was just talking about the kind of the protocol per se, let's say if you ran it over licensed spectrum.
If you ran 801AX, then you have to think about, so yes, there are people that are trying to do things like that, but then you have to ask the question about is there an economies of scale? So with 3GPP, we can drive economies of scale. You can get CPEs for less than $100 today. Now you have to ask yourself, can you do that with another technology? If you're going to have something proprietary, you may have those types of issues. You may have single vendor lock-in, higher prices. So at the end of the day, it's actually about business cases, right? I mean, we're investing money in the network. Are we making enough to recover our costs and make a profit? And there you have a challenge with those proprietary technologies, I think.
There's another question over there.
When you did your study in Denver, Mohammed, did you see any problems with interference that were in all your test cycles?
Luckily in Denver, we did not see this. We had SCTE use a whole 150 megahertz in Denver, so we could manage it. We did not see this interference. But with ICDs that we're already part of, I'm sure you know that we're doing like a big trial, part of this ICD, we may see this interference. But in Denver, no, we have not seen it. We had a full 150 megahertz to play with and explore, and it was more about understanding like coverage, different technologies to use.
So, BJ, maybe you can comment, but how would you manage this going forward with unintended future changes in unlicensed bands, interference, right?
No, it's an interesting topic. It's the moment it's shared and it's free, everybody can use it. And you could use, to the earlier question, non-3GPP compliant equipment. It doesn't have to be 3GPP. It doesn't have massive MIMO, but somebody could come in and blast away. The good thing that the framework that's been put in place with CBRS, with the spectrum allocation system, the SAS, I may be butchering the acronym, but the idea is that there is the energy detection, there is an allocation for, within that specific frequency. There's always an allocation for, this is when you transmit, this is when you don't transmit, allocation of the frequencies. But unfortunately, there comes a point that when we have more and more people on, there's only so much spectrum you can allocate. If you have 10 people in a given area, and that's more prevalent in suburban, where the density is higher. Not so in rural, with some of the problems you're trying to solve. Then you have to tell people to back off their power. So there's no free lunch, unfortunately. They're going to hit that point that this is the amount of spectrum that we have. I can start giving you slots so you can provide your service, but then once there's not much spectrum to go around, everybody sort of back off a tiny bit so nobody interferes with each other. What I feel to get into that point is that's where the PAL licenses come into play. You want to start guaranteeing a certain amount of service for your subscribers. So if you're really serious about this business, then you buy 10 megahertz of spectrum at least, and then the opportunistic GAA spectrum, you just add on to it to make sure you give your 25 and then above, which is my view of the world. Did I answer your question?
Yeah, thanks. And I guess it does kind of resonate with, it's less of a problem in rural areas, which is probably where your target, is anyway, right?
Correct. To be perfectly honest, for the cable folk, it doesn't make sense to try and target a fixed wireless access service in dense urban areas because we've got our wires everywhere. We're good to go. It's just there are different arguments to be made on the MVNO side of the house and trying to offload as much as possible because both Comcast and Charter have big MVNOs and so do other cable operators. But that's a whole different discussion. Yes.
Just kind of adding on to that, I guess, thinking about how the SaaSes are going to work. We'll ask about three different parts of it. One, are there features that you're expecting from the SaaS providers that really will be helpful in managing this? And I guess the second side of that is, what are you expecting from the cost side from the SaaS providers? And then that leads into, is there any difference between the different SaaS providers?
I can answer the second question. Yes, everybody obviously, if you look at that, is all the SaaS providers they're trying to make new entrants, right? You get the likes of Google, you get Federated. There's a new area of opportunity. So when there's an opportunity, people try to make money, a lot of money. That can be a bit restrictive for this service to be deployed. And so I think there are active negotiations going on with the people who are entering into this space and trying to bring that cost down, because the moment you start putting in, to Mo and Kashif's point, you could have a lot of devices out there to make the business case work. And if there's a cost per device that you're connecting to the SaaS, you have to keep that cost down. So we have the challenge of increasing the number of devices to make the business work, but if the SaaS is going to charge a whole lot of money for each device, then you've got to manage. So there's a balance that's been sought after right now. And obviously with multiple SaaS providers coming into the market, there is opportunity to start to negotiate that down. But the first question about which features that you would look for, I would defer to Kashif and Mo to give your comments on that one.
I can talk about this. So the good thing that FCC did here, as you know, is they are not managing themselves. They have private entities managing the spectrum with SAS, and the hope is that when there's competition, there is innovation. We see that at least 3 or 4 SaaS providers are out there, and they work with you to solve your particular problem, and also to provide you some value-added features on top of the regular SaaS functionality that will help you to get what you're really looking for. And we're not a SaaS provider, so I can't talk about those features, but I can tell you that in our discussion with the SaaS providers, they do have those features.
And sorry, Kashif. I just want to note that SaaS will not protect a GAA license. It will protect you if you have a PAL license. The GAA SAS will not protect the license holder. But to Kashif's point, yes, there is a lot of innovation we're seeing. We're working particularly with one SaaS vendor, and there's like a lot of cooperation between us and some features that we want to implement, and they are adding them.
Yeah, and one point here is, even though we talk about GA as unlicensed spectrum, it is not like 5 gigahertz unlicensed. It is unlicensed, but the interference is managed by the SAS. So if the SAS understands that there's 5 entities in an area that want to use 150 megahertz of spectrum, it will assign spectrum in such a way that interference is minimized proactively. So there's some of that. So I'd like to call it more lightly licensed than unlicensed, even for GA.
And this one feature that we've got to be aware of is in terms of managing interference. This is the first time in the US you're seeing a big chunk of TDD spectrum. And it's not like FDD, you have a separate uplink or separate downlink you can do, but there's a big chunk of TDD spectrum. What's really key in TDD spectrum is to make sure everybody transmits and receives at the same time. And the amount of time you allocate within that transmit, the slots you allocate, they're all synchronized. The moment you start allocating, if people have a different configuration, even though I allocate you this chunk of spectrum, the adjacent channel operation becomes a problem. You can't have guy sitting over here transmitting while this guy here, people on this block are receiving. You're going to start interfering. And then the earlier problem you talked about managing the cell radius, and your cell radius is going to shrink. Now, there's another problem coming our way. Just north of CBRS spectrum is the C-band spectrum. So the SAS today manages that configuration. It manages, hey, this is the allocation we're going to have across this band. And then you'll tell you, hey, I give you the 20 megahertz here, but by the way, this is when you transmit and this is when you receive. And we do all of that. But the moment you start expanding the C-band side of the house, which is the next primo real estate in spectrum that's coming our way, you need to make sure that synchronization ties all the way across. Because it's a snowball effect. You can't have a different configuration to your right, to the what's on the left in terms of frequency, and then you got to make sure everybody lines up nicely. So there are you will probably see interesting debate on that further down the track in the next coming years. I think we have time for one last question. Yeah, go for it. Absolutely.
I recently read an IHS market report, this guy, analyst Stephen Terrell, and he was somewhat down on the FWA business case, and he replayed this story about the LMDS, like, we've been here before, and he reminded us that virtually all the LMDS, people went bankrupt, and then and Verizon got all the spectrum. But I guess the point of this session is that, from the technology point of view and the spectrum point of view, things have changed. I mean, in that particular report, he remained kind of particularly negative on that, citing the LMDS experience. So I don't know if you have any comment.
Yeah, I mean, as you say, LMDS was more than 10 years ago, right? And since then, technology has changed. At that point in time, if you were doing, 1 bits per hertz, we're doing a lot more right now. So that obviously impacts the business cases. And then there's also more experience with fixed wireless. As I said, we're not doing it the first time in the US. There's actually existing operators in the US that do fixed wireless, but there are also operators in other countries. We talked about Australia. We have been engaging with operators in countries where home broadband doesn't exist because the wireline infrastructure is not present. And there we see great adoption for fixed wireless access. There is no option but to do fixed wireless because there is no infrastructure that currently exists. And the operators there are actually making money. They have a good business case for fixed wireless access. So I'll challenge Mr. Terrell on his article on that because we see our operators out there actually doing well with fixed wireless.
And one last thing I would like to add to that, there was a paper that's actually being submitted. It should be in the whole, where you can find them, where my team demonstrated how you can bring the TCO down using millimeter wave, the 28 gigahertz specifically, because using things like repeaters, so you don't have to have towers everywhere. So in dense urban areas, you can bring the TCO down by 30-40%. Because the beauty of it is, unlike an LMDA solution, this reflects, millimeter wave frequencies reflect really well. They are coverage limited, not capacity limited. If there are solutions that you can put in to bridge that coverage gap, there's a ton of spectrum real estate out there that you can, that you can use really well. And then we did mobility on 28 gigahertz. So that, there are things that are, to Kashif's point, there are solutions, there are technology innovations that are coming our way that make, some of those higher frequencies even more usable. Well, that brings us to the end of the session. Thank you so much for being with us today. Thank you, guys.
Thank you.
Thanks for the question.